Yesterday, if I can summarize what I did, what I tried to show you on the fusion flames, I first show you that um, if the Lewis numbers are equal to 1 for unity Lewis numbers, then one can solve the entire problem using in the large Dam-Kohler limit, namely when everything is consumed, or maybe the limit, if you like, of complete combustion, simply from the coupling function. If the Lewis number are not 1, then we derive some jump relation across the reaction zone, and we can then solve the entire problem, again, in that limit of complete combustion, um, uh, with the help of the jump relation. And what at the end I showed you is that, okay, those jump relation gives you some discontinuities in slopes um, in across the reaction zone, but there is an appropriate um, structure which we derived by stretching the coordinate in the normal direction to the reaction sheet. And we have seen that the scale or the thickness of this zone goes like the the Dam-Kohler number to -1/3, okay? So it's a very thin reaction zone. And what I also showed you that in the reaction zone, essentially, it's primarily the mixing of the fuel and oxidizer that occur, because in the large Dam-Kohler number, without further assumption, then the reaction zone occur at a constant temperature. So it's like an isothermal reaction zone. And I indicated towards the end of that discussion that this structure always exists, no matter what problem. In other words, no matter what the outer conditions are, we can always derive this canonical equation that essentially show the mixing of one of the reactant and the other together, okay? And the solution always exists. But it is limited in the sense that this is really the summary of the few sentences that I just said. Here is the smoothing of the gradient, and occurs in a thickness of d to the -1/3. But the limitation is that it does not describe flame extinction, a phenomena which is typically occur in diffusion flame. So we are going to revise this discussion by not only looking at the large Dam-Kohler number, but also assuming that the activation energy, or the Zeldovich number, beta goes to infinity. In other words, beta is also large. D is large and beta is large. Now the process is similar to before, but because now we are allowing for the reaction, for those two parameters, we are also going to allow for, in the fuel region, there is no oxidizer to leading order, but there may be a little bit of oxidizer. In other words, there may be some oxidizer leaking through the reaction zone if what is occurring there is not a complete combustion. In other words, there will be some mixing, some burning, but some will leak through. And similarly, there will be some leak of fuel in the oxidizer region. So the yellow, the highlighted yellow elements are, let's say, the new elements from the previous discussion. Still, in this zone, there is no reaction, because the reaction occurs only in the reaction zone. And therefore, we solve reaction-free equation, just convective diffusive equation. By the way, I focused in this discussion, as well as yesterday, on the temperature and the species equation, it does not mean that the fluid mechanics is not important. Of course it is. It is embedded in the convective term. So for more general problem, you have to solve here more complicated equation. For simple one-dimensional, or that happened, for example, in the Burke-Schumann example that I showed you, that there was some element of the fluid mechanics, although simplified. Now, we do the same thing as we did before, but now we have to retain, as I said, the Dex term in the perturbation, because there may be some leakage of fuel in oxidizer. The leading term should be exactly the Burke-Schumann solution. So we know how to compute the leading term. And now the focus is on this, as well as what's going on in the reaction zone. So to discuss the reaction zone, we do exactly what we did before. We stretch the normal coordinate by a small parameter epsilon to be determined. And that's what we are going to do next. After the stretching, we introduce this transformation in the equation. And so the d by dn turn out to be d by d eta, and the convective term turn out to be always smaller. The reason for that is because the diffusion is second derivative, so you have 1 over epsilon squared. The convective is only 1 over epsilon. And by the way, I hidden in this discussion, which is not totally perhaps obvious or trivial, you know, when you have in general an interface like this, and you are considering the normal as one of your coordinate, really you are considering a different coordinate system which is attached to this point at the surface. And in fact, that coordinate system is not fixed. It's not like a Cartesian coordinates fixed in all 3 directions. So it's a moving coordinate. We refer to it as an intrinsic coordinate attached to the surface. And so even though I only showed the normal derivative, there are, of course, tangential derivatives and so on, but they don't enter the problem. That's why I didn't write them down. In general, those coordinates are not trivial. In boundary layer theory, for example, these were considered as the coordinates, say, if the boundary layer is not over a flat plate, over a curved surface, like a wing, for example, but then the wing is fixed, and those coordinates are defined over a fixed surface. The flame is moving, and so that adds a complication to write this equation. In one of my papers, I wrote them very explicitly. So then, when you do the balance here, note that in the reaction term, we have also the exponential term left. And if we want to retain the temperature dependence, then clearly epsilon has to be the reciprocal of beta. So this is one choice that you made based on this. And the second choice is to balance this relation. And again, it showed that the Damcolor number is going to be epsilon to the -3 in order for this relation to be balanced. And the d hat is the scaled Damcolor number. In other words, it's the original one multiplied by epsilon cubed. So this is the distinguished limit that we are looking at. And then we have a balance equation, which is this. It only differs from what we discussed yesterday by this exponential. But as you will see in a minute, it's very crucial or very important. So then the details are that you write similar equation for the fuel and oxidizer. Of course, they will be very similar except of the minus term and no heat release Q. And as I said before, with some quite not trivial, but interesting, or not interesting is not the word. Well, some transformation that you have to work a little bit to make it. Again, the problem can reduce to a single canonical problem. So no matter what the condition outside, the problem always reduced to this form, but now it has two coefficients, two parameters. I call them auxiliary parameters, delta and gamma. Gamma is not the ratio of specific heat here. It's whatever I will define soon. And the boundary conditions are similar to what you had before. So this is the boundary value problem that describes what's going on inside the reaction zone. Okay, what are these parameters? By the way, before we, well, no, actually, let's say what are these parameters. I'll make the comment later. So gamma turned out to be the difference in the gradient on the left and on the right. I said difference even though in the numerator there's a plus, but note that one of them is negative, one is then it's positive. So it's really how much more heat is transported to one side of the reaction zone as opposed to the other side. And in the denominator is in fact the sum of the two. Note, again, there is a minus, but one of the slope is negative, so it's always a positive quantity. It doesn't go to zero. So the parameter gamma fixes the amount of heat needed in a given condition. Given condition, I mean given the outer solution. The second parameter is delta, which is essentially like a reduced Dam-Kohler number. In fact, before I tell you what it is, if you take delta goes to infinity, delta to the minus third go to zero, and you get exactly the structure of the Birch-Schumann flame. And so delta turned out to be, as I said, related to the amount of, or the available enthalpy at the reaction zone, which is associated with, you see, T1, YO1, YF1. In other words, how much incomplete combustion occur, okay? YF1, YO1 are essentially the amount that leak through or proportional to, and T1 is the drop in flame temperature. So if I know those parameters, I can integrate the problem numerically. It cannot be done analytically, you do it numerically, but it's a simple ODE, and you can do it for a variety of delta and gamma, and basically that's the type of curve that you get that satisfy those slopes. But note, the slope have to go to -1 and 1, but the distance from the 1 and -1 mark the, I call them S1 and S2. As you see in a minute, those can be determined from the numerical integration. And as you'll see in a minute, they are related to the extent of leakage that you have of fuel and oxidizer. So I know the details are a little involved, but or complicated, but you have to, look at the perhaps the reference to fully grasp the idea. Also, the problem has some symmetry. In other words, if you replace gamma with negative gamma and zeta with negative zeta, you get the same answer. It's not difficult to see that from just replacing those in the equation. So gamma equal to 0 is a symmetric problem, and then you will see that gamma positive and negative gives you different form. So, and here is what I said about the leakage. The amount of fuel on the positive side, which for me it's the oxidizer, is given by this function SF, which is either S1 or S2, depending on the value of gamma because of that symmetry. And the amount of oxidizer that leak through is related to SO, which is either S2 or S1. So there is this kind of symmetry. And this is some numerical integration. I start with gamma equal to 0. And let's start with the delta equal to 10. So delta is very large, equal to 10. It's this purple curve here. And you see that it's very similar to what we have talked about, the Birch-Schumann limit, right? It's simply connect the two slopes. As you decrease the Dam-Kohler number, so you move to this light blue curve for delta equal to 2, and then to delta equal to 1, and delta equal to 0.9, and then this value here, delta equal to 0.849, whatever, dot, depending on the accuracy of the numerics. If you try to lower it below this, you find there is no solution. However, for the values that I indicated here, you tend to see that there is another solution. In other words, for 0.9, there are two solutions. For 1, there are two solutions. And similarly for the bigger value, except that you see for, say, delta equal to 2, the second solution is here. So I didn't put it in the graph anymore. So the outcome is that the solution is multi-valued. For every delta which is bigger than some critical one, there are two solutions. For delta equal to the critical, there is a unique solution. For delta less than that, there is no solution. And as I indicated, as I started, delta goes to infinity, or large delta is essentially the Birch-Schumann solution. And if you look for, this was for gamma equal to 0. So gamma equal to 0 gives you that there is the same leakage on the left and on the right, and that's the symmetric case. And for different gamma, you see that there is breaks the symmetry. There's either more fuel leakage or more oxidizer leakage. Okay. So there's no point to go back to discuss each of these curves. They still have the same thing, that there is a critical value, which I indicated everywhere by the red curve, and multiple solutions otherwise. So what's the implication on this? Because from these curves, we can also compute the flame temperature, right? But here comes a question, what is the flame temperature? What value you choose the flame temperature? Because you have a reaction zone that spans, well, it's not a big distance in the original coordinate, but so you have a choice what you call it. Doesn't really matter much. It's qualitatively the same if you choose it at the maximum or based on some other criteria at slightly different point, okay? So essentially, let's say that's the flame temperature, or the temperature where those curves peak. It's a reasonable assumption. And so you can plot the flame temperature as a function of the Dam-Kohler number, which is captured from this delta. So clearly, when D goes to infinity, you have to reach the stoichiometric temperature, which is the temperature of complete combustion, or the Birch-Schumann solution. As you reduce the Dam-Kohler number, remember there are two solutions. I didn't show the other one here because very usually they tend to be quite separated, but at least in this region you see the two solution, the two solution, the two solution. And when you reduce delta below a certain value, there is no solution. So this point is the point where we can identify or relate to extinction, okay? In other words, no possible steady solution exists for delta below or for D below delta extinction, and that's extinction. Just as a general comment, I don't want to elaborate on it, but one can argue that, okay, that's a so-called static extinction. In other words, it tells you if solution exists or doesn't exist. Maybe if you do a time-dependent problem, solution can exist a little more or a little less than that. It's true, And it's more difficult to determine because then you have to specify an initial value problem or some specific initial condition. But it has been shown that when this happened, the extinction can occur sometimes a little bit before, sometimes a little after. Nevertheless, it's qualitatively gives you the correct picture. Okay. What's the comment here? Oh, there is a minor comment that de-extinction does not correspond necessarily to delta critical, but there is a relation between the two, which is really built on that distinguished limit that I indicated, can be determined. Okay, and this is just a graph of the amount of leakage. Note when gamma is positive, S1 is the fuel leakage or proportional to the fuel leakage. S2 is proportional to the oxidizer leakage. And you can see that S1, look at the scale 0 to 15, here is 0 to 1.5. By the way, 15 doesn't mean the mass fraction is 15 because it's still multiplied by the small parameter and some other factors. So this is just a scaled version of it. And, but here it's much smaller. So there is greater leakage of fuel because more heat is conducted towards the oxidizer side and vice versa here. So anyway, you can discuss those further. So this was more or less the end of yesterday's talk. And, or I don't know, yesterday or today, but I will continue on the fusion flames and perhaps even make, I'll pick and choose what I will show. So the first thing I want quickly to go over the example, which is a counterflow flame. It's a very common problem study in diffusion flames. Two colliding jets, one with fuel and one with oxidizer, are impinging. The two jets are impinging towards each other. And a flame gets established somewhere in that stagnation point flow. It is common, I mean, you see, I put a flat flame, but how do I know that? First of all, I don't know that a priori. Experimentally, people have observed that a flat flame exists, and so it's a good thing to assume that it exists and to see if a solution exists. So maybe it was somewhat dictated from observation, or maybe was assumed before, but this is the origin of that. And so, but it's quite clear that when you're close to the stagnation point, that's going to occur. Now, stagnation point is usually occur when a flow go past a bluff body. So it doesn't, the stagnation region will be only very near the nose of that body. Okay, so, and for starter, we're going to assume a constant density flow. So the flow is just given by minus 2 epsilon x, 2 epsilon y. And this is an axisymmetric configuration, I believe. And epsilon is the strain rate. I think it axisymmetric. Maybe it's two-dimensional. I don't know. I'll see in a minute what the slides will show me. So the fuel is coming from this end. We know what it is far at negative infinity, and we know the oxidizer far at plus infinity. And so the equation, yeah, it's two-dimensional. So the equations are written here. They are normalized more or less like before, but not exactly. I didn't want to change the normalization here because it will affect also the graphs, and I didn't want to reproduce them, frankly. The difference is that we have used the heat release Q to scale the temperature, okay? So the temperature, when it's approximately 1, it means that you are at the hot end, and in the unburned gas, it's going to be a small number, okay? So the unburned gas, I mean far upstream and downstream. So the equations, the difference in doing this is, of course, that there is an omega, omega, and minus omega. Don't get confused with the minus. The reason is that there was a minus here and a minus here, which I eliminated this minus. Usually minus is in the consumption, and positive it's in the heat, in the energy equation. But remember, the flow is minus 2 epsilon x. So there is a minus in the convection term. And of course, the diffusion has a minus term here. And so minus, minus, minus get eliminated. So, okay. The parameters are the Dam-Kohler number, which is related to the inverse of the strain rate. Okay? You change the flow, you change the strain rate, you change the Dam-Kohler number. All the other parameters are very similar to what we discussed yesterday. The first limit is d goes to 0, or d equal to 0, if you like. Often is referred to as the frozen limit. Frozen in terms of chemistry is frozen. Well, in here, unlike premixed combustion, there is a meaning to that. What it means is that the two fuel and oxygen mix, and there is just pure mixing. And so this is what you will see in pure mixing. And if the temperature far to the left, far to the right is given as the same, then it remains constant. If not, then there is some conduction, but that's secondary to the problem that we are interested. The next limit is the Dam-Kohler number go to infinity, and you can solve those equations. Instead of exponential, you get an error function. Basically, it's a function that increases from one constant to another, from negative infinity to plus infinity. If it's normalized, it goes from -1 to +1. And it's used to describe the proper concentration and temperature here. This is what you get with complete combustion. And if you integrate those equations, instead of using this analytical asymptotic result, you integrate numerically the full equation with the full chemistry, if you like. Full chemistry, I mean one step as described here. And you put a large D, and I don't remember what value was chosen. You see that the numerics show you curves that are smooth, but very close to what the asymptotic describe. Similarly for the temperature. Temperature has a sharp peak here, and so it's rounded. Yesterday, someone asked me the temperature I drew a concave and convex. It was a sketch. You see that in this problem, that's the type of temperature that you have. Okay, so we know this, and since we know those jump relation, we can substitute in here the solution and get an equation for the flame position. You see, XF is the flame, or the reaction zone. I say flame, but in this context, it's always reaction zone. So it's a reaction zone location. So XF is the location, everything else is known. Depending on the Lewis number, it depends on the initial mixture strength, and so on. And you can also obtain an equation for the flame temperature, and this is the stoichiometric temperature. The temperature at the stoichiometric surface. That's the definition. And of course, it depends on this location, XF. And for unity Lewis number, this expression simplified to just this, okay? Because this is e to the 0 is 1, and then you can manipulate this. So what you get, it's phi minus 1 divided by phi plus 1, which is graphed here. So it tells you that the flame is going to be on the fuel side, phi is less than 1 here. If phi is less than 1, if it's a lean mixture or a lean system, okay? And it's going to be on the oxidizer side if it's a rich system. It'll tell you on which of the two sides the flame would be. And the flame temperature is, in fact, exactly the adiabatic flame temperature as we discussed yesterday. However, when the Lewis number are not 1, then you see that there is a deviation. So, for example, the flame moves more towards the oxidizer side when the Lewis number is bigger than 1, and towards the fuel side when the Lewis number of the fuel is less than 1. And this graph was computed for Lewis number of the oxidizer equal to 1. Otherwise, you have just to maybe repeat, or maybe I didn't emphasize that enough, how does the Lewis number play a role here? You see, the Lewis numbers really show the competing effect of two things. Heat conducted away from the flame, and fuel or a certain reactant or mass diffusing towards the flame. And when Lewis number is 1, they are sort of, it's a symmetric situation, they are in balance. But when one is Lewis number less than 1 or bigger than 1, one of the two wins. So more heat get conducted away, it lowers the temperature, it leads to less complete burning. On the other hand, if the mass win, there's more fuel and oxidizer getting into the reaction zones and enhance the reaction. So you see the competing effect, that's how it plays a role. Okay, so you can also again see that you will get adiabatic temperature for phi equal to 1, which is the red curve, and super adiabatic flame for Lewis number less than 1, and sub-adiabatic temperature for Lewis number bigger than 1. And here is now the picture that we are, if you like, that we were able to compute. So we were able to begin with, we discussed the Birch-Schumann limit, and then we discussed the frozen limit. But those two are eventually, they connect when the Dam-Conner number increases from small number to large number. One possibility is that it connects like that, for example. And another possibility that it turns back and it creates an S-curve. And this is the more common one, really, in diffusion flame. It was first obtained numerically by Fendel in '65, numerically. And later it was shown that, as I have in fact described to you earlier, that the asymptotic limit gives you, in fact, the turning. Let's go back. Oops. Yeah. The asymptotic, in fact, gives you the turning of this part. I did not discuss the turning of this part, but in principle it can be discussed. What needs to be done is to extend the frozen limit to a very weak burning, and the weak burning keep on increasing as you increase the Dam-Conner number. But what happened here and here is really ignition and extinction. When you have a weak burning, keep on being weak and weak as you keep on increasing D, come a point here that the only solution have to jump to the upper branch, and the upper branch is very intense burning to the extent that it eventually go to the complete burning of Birch-Schumann. And if you start with the Birch-Schumann solution and decrease the Dam-Conner number, then, for example, by increasing the velocity, then eventually you come to a point that the only solution is dropping to the one below, which describe extinction. Okay? Now the problem was now analyzed, or I want to just give you a briefly description of what happened if gas expansion or density is not assumed constant. So now you have to solve the entire system of ODE. What happened, however, because of this particular configuration, the problem admits a similarity solution, namely a solution of the form that the axial velocity depends on x only, and the transverse is proportional to y. So can be written as u of x, y, v of x. When you substitute in the governing equation, you obtain a consistent mathematical problem that can be solved numerically. And essentially, this is what I want to describe to you. Note that in the absence of combustion, the problem is simply, the answer is just 2x and 2y. The epsilon that I had before is just hidden in the scales. Okay, and what is this? I don't know why. Seems like I repeated that twice. Anyway, here are the results. First of all, I am showing the effect of the Lewis numbers. The dash curve are the asymptotic result. These curves are the numeric. Basically, if you go through those graphs, and I'm not going to discuss each of them separately, you will see that it's the same picture that I showed you before is obtained also numerically with some differences. Same thing here about the location of the sheet, if it's on the fuel side, the oxidizer side, and same thing about the fuel leakage, which we computed here also numerically. Okay, and this is what I wanted really to emphasize, which is the flow field. So if there is no combustion, essentially the solution is this dashed curve here, which was, remember, just proportional to x. Okay? Now, with combustion, what happened is that the axial velocity go up, down. Of course, this is the stagnation point, so it has to go to 0, and then it does that. And so what really happened is that some vorticity or a rotational flow is formed near the reaction zone, and it spread, it push, if you like, the incoming gas to the left and to the right, and those are known or represent some flow displacement. So you can see here that the displacement is more significant, and here the vorticity is more significant when the heat release is larger. Again, those value of Q are different maybe than the one that you have seen before. It's just due to scaling, that's all. Okay, this is just to show you the previous line, the displacement of the fuel side, the oxidizer side. It's a detail. Okay, so the next thing I want to discuss is the mixture fraction formulation. So in premixed combustion, fuel and oxidizer ratio or equivalence ratio is fixed by the amount that fuel and oxidizer that you put in the system. And as a result, the progress of combustion can be described by the extent that the mixture is completed burn or incompleted burn. In a non-premixed combustion, something which can be used similarly, but it's not identical, as the equivalence ratio is this mixture fraction, Z. It's not the same, but can be related. And I'm not going to show that part, but I will talk about what is the mixture fraction. So first of all, the mixture fraction is defined such that this coefficient, Z, the mixture fraction, is equal to 0 in the oxidizer side and equal to 1 in the fuel side or in the fuel stream. So depending on the geometric configuration, you're going to have for example, this is a mixing layer. You have fuel and oxidizer here separated by some plate. And when they, beyond the end of the plate, they start mixing and burning. So clearly far up, there will be Z equal to 0 because it's the oxidizer stream. Far away, there is no fuel. And far down, Z equal to 1 because it's only fuel. Similarly, if you have a jet, then Z equal to 1 will be where the stream of the fuel come, and Z equal to 0, say, on the two other sides. So I'm just illustrating what is, these two limits. Or Z equal to 0 is going to be in the oxidizer side, Z equal to 1 on the fuel side in the counterflow. And so here is the definition of the mixture fraction. And it can be generalized, if it's not a fuel plus oxidizer go-to product. So if you're interested in that, you should look in the literature. But the idea is here. And you can see that that's correct, what I said. If on the fuel stream, this is not 0, but there is no oxidizer. YO is 0. So you get nu YF plus YO2 divided by the same thing, so Z is 1. On the oxidizer side, there is no fuel. So what you get is YO2 minus YO2 is equal to 0, right? So that's the definition. Okay, so now how does this work? Oh, first, I also want to indicate that I can rewrite this in terms of what I refer to as the mixture strength, and I denoted it by phi. The mixture strength was the amount of fuel here and the amount of oxidizer here divided by the stoichiometric proportion of this fuel and oxidizer. Or the amount of fuel here and the amount of oxidizer here divided. So it's not an equivalence ratio because they are two separated, but some kind of measure of lean-rich system. Okay. So if you define phi, clearly you see that there is a ratio here, so you have to divide by YO2, both numerator and denominator, so you get the phi from here plus 1, and you can see that simple algebra gives you that form as well. I don't know if I'll use this or this, but they are related. So that's the definition of Z. Now, how is that relevant? So here is the equation for the mass fraction of fuel. Here is the equation of mass fraction of the oxidizer. And the mixture fraction Z is essentially the difference between nu multiplied by YF minus YO. The rest is a constant. So when you differentiate, the constant doesn't matter. So if you multiply this by nu and you subtract from here, of course, there is a typo here that should be nu O, and nu was defined as nu O WO divided by nu F WF. So that's obvious. Then when you subtract them, you get this equation. So what you have is dz by dt minus rho, say df. I chose df, but I could have written that as do, and here the difference will be with a minus sign. Multiplied by the Laplacian of yo. In other words, it's not a conserved quantity yet, but if the diffusivities are the same, the right-hand side go to 0, and Z is a conserved quantity, okay? So when there is a common diffusivity, then between the fuel and oxidizer, then Z is a conserved scalar. Someone asked me something about the terms preferential and differential diffusion. What's the difference or what's what? And the answer is depend on you what you want to call what. But the idea is that there are two things. There is a Lewis number, which is a ratio of thermal diffusivity to mass diffusivity. In other words, there is some differential diffusion between heat and mass expressed by Lewis number. But there is also different diffusivity between fuel and oxidizer, which is preferential diffusion of one or the other. Of course, you can call differential this and preferential this. I used to always refer differential diffusion, heat and mass, preferential between fuel and oxidizer. I haven't seen any clear terminology elsewhere, but there are some people that use that in both directions. So just as a minor comment. So anyway, if the diffusion are the same, then Z is a conserved scalar. And the nice thing about it is that similar to the fuel, similar to the oxidizer, when there is no chemistry, for example, in the case of frozen chemistry, when it's 0, 0, then all of them have the same mathematical equation. The operator operating on YF, YO, or Z is the same. And so, so what this implies is that any of the YF, or YO, with respect, essentially is a linear function of Z, simple words. You can see it also mathematically here. If you do a transformation, this is 0, and you end up with a second derivative of yi with respect to Z equal to 0, which is a linear function. So if YO start at YO2, it must go to 0 on the fuel side, and YF1 is start here, it must go to 0 on the oxidizer side, and so that's what the description of the mass fraction in terms of Z. This is for frozen combustion. What happens if you have, with the temperature, you cannot do that unless you also assume that lambda over Cp is rho d. In other words, the Lewis number is 1. So if before I use preferential diffusion equal to diffusivity, now you also, if the Lewis number is 1, then also T can be expressed in terms of Z, and then it's going to be a linear function from T1 to T2 or T2 to T1, depending on the direction. Okay? So that's nice for frozen limit. What about the other limit, complete combustion? Well, it's also true that, that these equations are equal to 0 on the right-hand side, either on the fuel side or on the oxidizer side. And so, therefore, it is true that on one side or on another, the yi, the different y, are also linear function of Z. And so if they are linear function of Z, here they are. This is the oxidizer and this is the fuel. And since they are completely consumed at some location, that location is the stoichiometric Z. So it's the stoichiometric surface is determined by this condition. Okay? And now what about the temperature? Okay, if the temperature, in general, the temperature cannot be expressed in Z, but if the Lewis number is 1, yes, for the same reason. And then the way to obtain it in a simple way is to write the coupling function t plus yf and t plus yo, and then you can, since t is a linear function of z, yf is a linear function of z, the h's are a linear function of z, and when you write them and then you assume that in the fuel side there is no oxidizer, and the oxidizer side there is no fuel, you obtain the temperature in terms of z. So you obtain that relation, which I will show a graph in a minute. But you can also evaluate the flame temperature by evaluating either the top line or the bottom line, which should be equal to the same quantity when z is equal to z stoichiometry, namely where the reaction sheet is. And this is the flame temperature or the stoichiometric temperature. And it is, in fact, the adiabatic flame temperature in this case. It's a little different than what I have shown you before, only because I have assumed here that the temperature T1 and T2 are not necessarily the same. If it's the same T, you reduce to the previous equation. It is the adiabatic flame temperature because we have assumed unity Lewis numbers, okay? So remember that. Otherwise, that's not the formula. We have seen that the flame temperature depends on the Lewis number otherwise. So this is the graph of T, of YF, YO, and so on. So why is this useful? Well, if the combustion does not vary so much in one direction, then you can essentially change your coordinate and call that direction z, and somehow it tells you the distribution in z. But it's not exact unless that the combustion does exactly in that direction. I will show you soon an example. In a simple situation like the counterflow, for example, you can express the z equation is this, and you can solve it. Remember, the equation for z is just an operator, the same as the fuel oxidizer temperature equal to 0. And for unity Lewis number, or one common d if you want, and you can compute z. So what's the difference between using z or the coordinate x that we had in the graphs before? It's just contracting the minus infinity to infinity into 0 to 1. So in this situation, it's a simple transformation, nothing too exciting. But the idea is that it could be useful in more perhaps general situation. For example, here, if z does not change very much. But in this flow, which is separated by a plate, then and you have a flame, which I will discuss in the next lecture, the nature of this flame, then you see the real curve z are curved like this. So if you want to change to a coordinate, one of the coordinates to be z, then it's not exactly the same as y, but maybe it gives some indication of what happened far to up and far down in terms of the combustion field. Okay, I will, maybe one more thing. It's actually interesting. Suppose that I change my coordinate system and use z as one of the coordinates. So I can compute the normal, which you see on the blackboard, from that coordinate. And the normal is going to be essentially d by dz multiplied by the gradient of z, because the normal is defined, if I know z, I can use z stoichiometry as the surface from which I can compute the normal. If I do that, the details are that in the reaction zone structure that I showed you before, instead of variation in the normal direction, you're going to have variation in the direction of normal to the stoichiometric surface, which can be a little different. And the gradient appear here as a gradient square, and it has been referred to in the literature as a dissipation rate, or an instantaneous dissipation rate. Anyway, the idea is that you can compute this, and since we know that when the Dam-Kohler number decreases below a critical value, you have extinction, then you can argue that the extinction occurs because this appears in the denominator, then if C, or if the dissipation rate is above some value, you have extinction. It's an equivalent description, nothing qualitatively different. That's the end of this story. That's a good time for